So next we're going to talk about binary stars, and in particular how they evolve. And first I just want to remind you that we talked about the Roche limit and Lagrange points a little earlier in the semester. So remember, the Roche limit is how close something can approach before it's tidally ripped apart. And the Roche lobe is a similar sort of idea, and it has to do with the gravitational potential, and it's a gravitational potential surface in a system of two orbiting massive bodies. And we talked about the Lagrange point before, so basically you've got a point in between the two stars where gravity is completely balanced out from one to the other. Okay, and so one of the things that's interesting about binary stars is that unless the stars are exactly the same mass and composition, they will evolve at different rates. And then what happens to them will depend on their separation and on their relative masses. And so we're going to have a look at the different types of evolution that can happen with binary stars. So we already talked about the Roche lobe, and basically what you can think of it as being is that you've got the star in the middle of here, but basically anything inside of here really belongs to the star. It's going to have to be moving pretty fast to escape from this zone. And anything inside of this sphere here, this lobe, belongs to this star. And you've got this point in between, which again is the Lagrange point where the gravitational forces are equal. So this is just a 2D view of that. So here I've got a binary system, and this is called a detached binary. So the star is wholly within its Roche lobe. So you've got this Roche lobe, but the star is right within it. It's got a Lagrange point between the two. So here I've got a blue star and a yellow star. This one's less massive, so its Roche lobe is smaller. This one is more massive, its Roche lobe is bigger. But that's a detached binary. Then we have semi-detached, and so this is basically where you've got one of your stars is filling up its Roche lobe. It's so big that its Roche lobe is inside the star, and so basically it means that because this is a surface of equipotential in gravity, then material basically gets funneled through the Lagrange point and towards the other star, and so you get this transfer of material from the bigger, the one that's exceeding its Roche lobe. It's also possible that both stars will exceed their Roche lobes, in which case you get what's called a common envelope phase. And so you can have something that is, it's called a contact binary, because essentially there is nothing between the stars. They have cores, but then their envelopes both exceed their Roche lobes, and so they basically merge into each other. And this may be important for the development of axisymmetric structures for planetary nebulae, although that's still under discussion in the field. But then remember that stars evolve, so they may be in one state at one point in their lives and then they change. And so here we're going to consider the system Algol. Algol is probably one of the most famous binary systems. It's been observed for centuries. And it's thought that it's basically a semi-detached binary, but it's thought to have started out as just a regular binary. So you've got a blue star and a solar mass star. So you've got a yellow star and a blue star, and they've got their Roche lobes, and they're rotating around each other, and they are completely detached. There's no mass transfer between them. But then the blue star is going to become a red star. Remember, they evolve to a red giant phase regardless. I mean, they're actually a red supergiant phase if they start off blue. But they're going to go over to the red side and become really big, because that's what happens when you run out of hydrogen in the core. But that means that this star that was well within its Roche lobe exceeds its Roche lobe, and material starts to flow onto this solar mass star. Well, that means that this solar mass star, which is still a main sequence star, because it doesn't evolve as fast, the blue star evolves much, much faster than the yellow star. So it's now gaining mass to the point where it will become a massive star, and you also have lost so much mass from this side that this is now a red subgiant, and this is now a massive blue giant. And so this one will now evolve quickly again, and it will exceed its Roche lobe, and they will probably go through a common envelope phase at some point in the future. So just to reiterate this, we've got a star, it expands beyond its Roche lobe, and it is, so here I've got two stars, they're no longer outside the Roche lobe, but this one, so here in this case this is considering a white dwarf, so this is the idea for Type 1a supernovae. We've got a white dwarf here, we've got a main sequence star here that's low mass, It becomes a red giant. It's still fine. It becomes a red giant again. Now it fills its Roche lobe and material is flowing onto the star, and this will feed it material and feed it heat until eventually it can destroy itself in a thermonuclear explosion. Okay, so just to reiterate this point, we've got a white dwarf. It's got material that's being accreted onto it. So material is coming off of one star onto the other, but angular momentum has to be conserved. So just like the collapse of a cloud gives rise to a planet-forming disk, the collapse, the contraction of this material and collapse onto the star leads to what's called an accretion disk. It's accreting onto the star, and it will be a disk, but it's also heating up hugely. And so what you have is that this material here is actually about 1,000,000 Kelvin, which means that it's giving off X-rays just because of its temperature. And so we have what's called an X-ray binary, which is where the material that's being sucked onto the white dwarf is being heated so much that we see strong X-ray emission from it. There's another thing that can happen, which is a nova, which is slightly different than a supernova. So this is just an example of one. Here you can see there's the star as it was, and that's what it looked like when it exploded, when it started to increase in brightness as a nova. And in this case, what happens is that it's mostly hydrogen that's flowing from one star to another, and it accumulates on the surface, and then when it gets hot enough and dense enough, it can actually fuse even on the surface. Remember that we're talking about the core of a star. So originally when it was a star in the AGB phase, there was hydrogen burning going on around this thing. And so now you're going to do it on the surface of the white dwarf. And so you get this explosive hydrogen fusion on the surface of the star, but it doesn't destroy the star. It only happens on the surface. So you get this brightening of the star, which then fades, and we call this a nova explosion. So there's a couple of examples of these. There's R. Aquarius and T. Pyxidis. And usually what happens is these are what's known as recurrent novae. So you've got this system that is funneling material onto the surface of a white dwarf, and then it sets off fusion reactions. Fusion reactions eventually die off because there's nothing to sustain them, and then more mass is transferred from the companion star. So you get this cycle, and it'll be every few years or decades that you'll then get a brightening episode, an episode of explosion on the surface. Okay, so what is the difference between nova and supernova? They're both white dwarfs that have companions, and they're both systems in which material is flowing from the companion onto the white dwarf and giving rise to explosions. The difference is that for a nova, the white dwarf is not close to the Chandrasekhar limit. So remember, for a solar mass star, you get a 0.6 solar mass white dwarf. Well, that's nowhere near the Chandrasekhar limit, and so you can actually do quite a lot on the surface before you're going to get close to causing there to be an explosion. You have to be pretty close to the Chandrasekhar limit before you can get ignition inside of the core, the carbon core. But if you've got something that's high mass, that's 1.3 solar masses, then the energy from hydrogen burning doesn't need to put in that much in order to overcome that electron degeneracy. That is to make it switch on the explosive carbon burning. And it is this carbon burning that gives us the elements, actually beyond iron as well. Supernovae make all elements, and low mass stars make elements up to lead, but type 1a supernovae make iron very effectively. Whereas in a nova, the star isn't destroyed, you're not throwing material, you throw some material out in space, but you're not throwing out all that stuff that was in the star, and so the fusion just stays on the surface. So that's it for novae, and we're going to talk about neutron stars and black holes shortly.